So continuing our discussion on rational functions from today, I guess, we're going to talk today about finding vertical asymptotes. And we saw all kinds of rational functions today in class, and all of them had these characteristic asymptotes all over the place. And from the graph, it's not that hard to figure out where they are, right? They stand out pretty well, just an asymptote. But how can we figure them out from the equation, right? So just by looking at the equation, we should be able to determine where my graph is going to have an asymptote. Okay, and that's sort of the goal for the day. So let's jump right into it. Let's look at the most basic of all rational functions, which is f of x equals 1 over x. Can't get more simple than that, right? 1 over x. Well, before I look at the graph and figure out where the asymptotes are, I want to think for a second about what would happen if I plugged in a 0 for x here, right? What would f of 0 be? Well, obviously it would be 1 over 0, but that doesn't exist, right? It's undefined. So 1 divided by 0, you can't divide by 0. How many times does 0 go into 1? Well, you can't answer that question, right? You can multiply 0 by any number, no matter how big, and you're never going to get to 1. It's always just going to be 0. So 1 over 0, 1 divided by 0, is undefined. It doesn't exist. So my question to you is, what does that mean graphically speaking? Yeah, f of 0 is undefined, but if I look at the graph, what does that actually mean? Well, let's pull up the graph real quick. So let's go to Desmos, and here it is. F of x is 1 over x. Well, look at when x is equal to 0. What I have right here is what we call a vertical asymptote, okay? No matter how close I get, I'll never actually touch that line x equals 0, okay? And I can get really close. Like you can look up here when I'm way up here, okay? You can see there's still that tiny little gap between my graph, right, and the actual line x equals 0. I'm still not at 0. No matter how high I can go all the way up to, let's go up to 200 here, right? And if I zoom in enough, gosh, it looks like I'm on top of it, right? But if I keep zooming in, you can already see there's a little gap there. And if I zoom in even more, oh, I lost it. There it is. You can see I still haven't touched it. Even all the way up here at 181.75, I still have not touched the x-axis. And I never ever will, okay? That's my vertical asymptote. And it happened at x equals 0. Okay, now you might have some suspicion, since I showed you already that f of 0 was undefined, that has something to do with it. Okay, and in fact, you'd be right. You can't divide by 0, and the way that appears graphically is with a vertical asymptote. But we can actually see that not necessarily from looking at the graph, but just by picking values of for x and seeing what happens as I get really close to 0. So I don't actually do f of 0 because that is undefined. But what happens if I pick values that are really close to 0 and then see what happens? Okay, so like for example, we already saw this slide. For example, the closest number I could think of to 0 is 1. That's the closest whole number to 0. Okay, so what if x is 1 or 0.1 or 0.01 or 0.001 or 0.00001, right? So I'm getting so close to 0. This is a tenth, a hundredth, a thousandth, 1/10,000th, right? And then what's going to happen to f of x? So f of 1 is just going to be 1 over 1, which is just 1, right? So at 1, I'm at 1. So at my x-coordinate of 1, my y-coordinate is going to be 1. If x is 0.1, well, that's 1/10. 1 over 1/10 is just 10, okay? If x is 0.01, that's 100th. So 1 over 100th would be 100. And then 1 over 1,000th would be 1,000. And then 1 over 1/10,000th would be 10,000. And I could keep going like this forever. 1 over 1 millionth would be 1,000,000. And 1 over 1 billionth would be 1 billion. And as I get closer and closer to 0, smaller and smaller and smaller numbers, all that's going to happen to f of x is it's just going to get bigger and bigger and bigger. And we kind of saw that exact behavior when we saw that asymptotic behavior just a second ago for my graph, right? As I picked values that were closer and closer and closer to x equals 0, my f of x got incredibly huge. The same could be said if we approached it from the other way. So if we looked at -1 and -1/10 and -100th and -1,000th, well, the same trend we'll see, right? 1 over -1 is -1. 1 over -0.1 is -10, right? 1 over -0.01 is -100, and then -1,000, and then -10,000. So as I approach 0 from the other side, as I pick negative numbers getting closer and closer and closer to 0, my f of x is still going to get outrageously large. Well, technically outrageously small, right? Because now it's a negative number, right? So that's why I have an asymptote at x equals 0. Because first of all, f of x is undefined there. But second of all, if I pick numbers that are close to 0, my values for f of x are either going to get really, really high or really, really small, and this is why. Okay? Well, let's look at a slightly different rational function, a slightly more complicated one, something like 1 over x minus 3. Okay? Well, now if I plug in 0, I don't have a problem. 1 over 0 minus 3 is just negative 1/3. Okay? But I do have a problem at a different number. I can't plug a 3 into this equation. Because if I plug a 3 in, I'll get 1 over 3 minus 3, which is, of course, 1 over 0, which is undefined. But let's think about numbers that are close to 3. Okay? So if I try numbers like 4, and then 3.1, 3.01, 3.001, 3.0001. And I plug those into f of x. Well, if I plug a 4 in, I'm going to get 1 over 4 minus 3. That's 1 over 1, so that's 1. And then I'm going to get 1 over 0.1, so that's 10, and then 100, and then 1,000, and then 10,000, right? So it's almost exactly the same as what I had for 1 over x, except for instead of now picking x's that are getting closer and closer to 0, hold on, let's go back, closer and closer to 0 like I had before, right? So closer and closer to 0. Now I'm picking numbers that are approaching 3 instead, and closer to 3. And the closer I get to 3, the more outrageously large my f of x becomes. Same thing if I go from the other side. So this was all numbers bigger than 3. Now if I pick numbers that are all smaller than 3, I see the same general trend, right? The closer I get to 3 from the other side, the more outrageously small my numbers get. So instead of going to 10,000, it's now negative 10,000. And then I would do negative 10 million and then 10 billion and so on, okay? So these are the points that I would have to plot to graph this. And then if you look at the graph, actually on Desmos, let's pull it up. 1 over x minus 3. In fact, you'll see there is a vertical asymptote right there at the line x equals 3. In fact, let's plot the line x equals 3. Okay, that's my vertical asymptote, that green line. No matter how close I get, I'll never actually touch the line x equals 3. Okay, and the reason why is two things. One, it's undefined. 1 over 3 minus 3 is undefined, so I can't actually have a point on that line. But you'll also notice that trend I was showing you on the table. As I approach 3, either from the right side or the left side, my graph is going to either shoot up or shoot down, but it'll never actually get to a value where x is equal to 3. Okay? So you probably are starting to see a pattern already. Okay? When the denominator is 0, that's when I expect I'll have a vertical asymptote. Okay? It doesn't even have to be as simple as 1 over x minus 3 or 1 over x minus 2 or 1 over x minus something. Take a look at something like this. Okay, 1 over x squared minus 9. All right, this is 1 over x plus 3 times x minus 3 because that's a difference of squares, so I factored it to x plus 3 and x minus 3. So if I pick values again, the same values that are getting closer and closer to 3, I should expect to see that same sort of asymptotic character. Whereas I plug these into f of x, I get numbers that are getting bigger and bigger and bigger and outrageously bigger. And you can check my math on this if you want, but like if I plug a 4 in here, it's going to be 1 over 16 minus 9, so that's 1/7, right? So that's a 0.143. And then if I plug a 3.1 into here, it's going to be a 1.69 or 649, and then 16, and then 166, and then 1,666.639. So again, it's getting bigger. It's getting bigger slowly, right? Compared to the last one where I was at 10,000 at this point. But if I keep picking numbers arbitrarily close to 3, I'm going to see the same trend. And same for the negatives, right? So you can check those numbers if you want, or just trust me. Now the thing is, this isn't the only place where my denominator would be equal to 0, right? When x is 3, surely my denominator would be 0. But also when x is negative 3, my denominator would be 0. And in fact, if we go and check out the graph for this one, this was 1 over x squared minus 9. And look at that. X equals 3 is still a vertical asymptote because, of course, at x equals 3, my denominator is 0, just like I saw a second ago. But if I do x equals negative 3, the other place that would make this denominator 0, let's plot that as well. X equals negative 3. And that yellow line is a vertical asymptote too. Okay, so my graph, my blue graph for my rational function, will never touch either of those lines. So this graph has two vertical asymptotes, but it's both of the places where the denominator is 0 because I can't divide by 0. And if I try to divide by 0, I'm either going to get, well, it's undefined, but if I try to divide by a number that's close to 0, I'm either going to get an outrageously large number, like these numbers here that are really close to 3, where my x values are really close to 3, or a really outrageously small number like these back here. Okay? So this is cool. We kind of have an idea of how to find vertical asymptotes now. If I just take my denominator and think about where it'll be 0, that's where I'm going to see this asymptotic character that I was talking about. So if I have something like this, 1 over x squared plus 2x minus 15. Well, I know that that factors into x plus 5 and x minus 3, right? So where do I expect to see vertical asymptotes? Well, at the places where my denominator would be 0. That would be at x equals negative 5 and x equals positive 3. So let's take a look at that one now. Okay, so let's take a look at that one. I'm not even going to bother with the table in this case. I'm just going to go straight to the graph. So I had 1 over x squared plus 2x minus 15. Okay, and lo and behold, there's my asymptote at x equals 3. The other one I expected would be at x equals negative 5, and there's that one. Okay, so my two asymptotes are again at exactly at the two places where my denominator would be equal to 0, negative 5 and positive 3. So that's a good trend to know. If the denominator is 0, then I'm going to have an asymptote there. The numerator could be anything. We've been using 1 just to make it simple, but I could change it to whatever I want. If it's 3, my asymptotes don't change. If it's 10, my asymptotes don't change. The shape of my graph changes, right? You can see sort of the difference. There's 1, that's 13. So the shape of the graph might change a little bit, but the asymptotes don't change because it's where the denominator is 0. Even if I make the numerator a different polynomial, because right now I'm just using constants. If I make it x, okay, again, the shape changed. See how I went from sort of this little sad man to this little, wavy thing here? The shape changed, right? But I can make it x plus 1 or x plus 3, right? Or anything I want. I can even make it a quadratic on top, right? So maybe it's x squared, okay? Still have the same vertical asymptotes because it's where the denominator is 0. I can make it x to the 3rd power. Okay, it's hard to see because you gotta zoom out more. Okay, all this weird stuff is happening, but the vertical asymptotes are staying the same. It's still x equals 3, x equals negative 5, right? I could do a cubic, let's do x cubed plus 3x squared minus 5x plus 20. Okay, and the graph changed all over the place, but it doesn't matter. The vertical asymptotes are still the same. I think the best way to look at this is also with sliders. So let's put some sliders in and we can kind of see. So I'll make that A, make that B, make that C, and then I'll call this D. Okay, and then I'll put sliders on everything. Okay, and now look, even no matter what I do to change those values, okay, and it changes my graph drastically when I do this, but my vertical asymptotes are always the exact same, no matter what that top polynomial looks like. Here, I'll zoom out a little more so you can see that there's still vertical asymptotes, right? So the graph changes all over the place, but the vertical asymptotes stay exactly the same. Okay, so